Hi everyone, so today I'm going to show you guys how to produce a simple yet effective time series forecast in Excel using nothing but the solver package and some handy formulas. But here's a preview of what it's going to look like. And I'm going to show you how to write the objective function, how to write the model or the formula, how to optimize the coefficients, and how to tune the results, basically. And just some practical guidance. Sometimes models like these quick turnaround times to produce something fast for upper management happens all the time, especially if you work, mostly close to, the C-suite or upper management, sort of in important roles. The farther you get up in the finance department, the more this happens where, you need a quick and dirty forecast that's still useful. And doing it in Excel in the way I'm going to show you today is very useful. It's a good thing to know how to do. It can come in handy. And it's very easy, and it's kind of satisfying if you're a Python user. I'm a heavy Python user, but writing it out in Excel is kind of fun. For some reason, everything happens dynamically and in front of your face. It's kind of like you're just puppet mastering the whole thing in front of you, which is kind of fun. So let's hop into the video. So I'm going to be using this time series starter data set from Kaggle. Let's just download it. I already downloaded it and was playing around with it, but I'm just going to download it again. So if you go to kaggle.com, you can just search for time series starter dataset. You can find this dataset here. It just has months of revenue. It's basically company revenue by month, and it has some other information there. We're mostly going to be looking at revenue by month. So let's go ahead and download this zip file here, and then I'll go over to my downloads, and it's right here. So I'm gonna just copy this, and I'm just gonna put it in like a new folder. I'll call it Excel Data Science Forecast. We'll drop that right in there, and let's just go ahead and open this guy. Okay, and it's a CSV file, so I'm going to save it as a proper Excel workbook, and I'll call it Excel manual. I'm going to call it Excel DS model, data science time series model. How about that? All right, so here's our data set. And what do we got? We got the period of time, which looks a little funny. All of the dates are prepended with 01 for some reason, but really these are months over time. The middle two digits is the month, and the final four is the year. So we'll parse that out into, just having what's it called, month year sort of situation. So I just froze the top row there so we can see it as we scroll. But here's the revenue column, and this is what we want to basically forecast into the future. If we scroll down, we'll see that starting in May 2020 and onward, there's no data, so we'd want to kind of populate that with the forecast. So let's go ahead and do this. I'm just going to get rid of these because we don't need them. And let's create a new month year column, and it's just going to be basically the month and year from there. So let's grab the month, which would be mid A2, 1, 2, 3, 4, length 2. So that gives us the month. And then, so we need, the year is easy. It's the right A24. And then we go like that. There we go. Let's drag this all the way down. So now we got all the dates. Let's make sure this is date type, which it is. Perfect. Did that work? Yeah, I'm doing my shortcuts over here, and this should be just type number. It's fine. Okay, so here we go. We have our data like this. So what I'm going to do now is I'm actually just going to plot this information. So I'm going to do this again. Select data here, B1. We want all the values. Perfect. Edit this. Perfect. There we go. All right. So a little bit of chart annoying stuff, but anyway, I have the dates on there now. That's all I wanted to do. All right, now let's start building this very simple time series data science forecasting model. So let's call it Rev Forecast, and we're gonna add this in as we go. But so what we want to do is go to the spot where we need to start building it, and what we essentially want to do is say, how are we going to build this forecast? Well, we're going to make an auto-regressive model. Auto-regressive means what? Means that the value we want to predict is going to be a linear combination of the prior month values. So I'll show you exactly what that means. It's basically just a linear regression model. So we're going to have an intercept term that we're going to call drift in the context of time series modeling. Drift is basically the intercept term. So drift, we're going to have let's call it AR1, AR2. This stands for autoregressive. Let's go to AR6, and then let's do an AR12 for like a seasonality thing. Let's randomly initialize these to have some random values there. And I'm just going to show them as a number. And then what I want to do here is, this is coef name, coef value. So the thing I like about Excel is how interactive it is. And if the data set's small enough, you can use it, and it's kind of fun. Python, you got to run the cell, view the output, update, whatever. But for interactive quick analyses, which are needed often when you're supporting like C-suite executives and stuff, and things need to be turned around kind of quickly, being able to spin up a data science quality model in Excel quickly is kind of valuable. So basically here, what we're going to do is construct this forecast for the month of May 2022. So what it's going to be, we're going to take the last 6 values of actuals, put them right there. And then what we're going to do is do a sum product of that with our coefficients, our 6 coefficients. We need to make sure we lock those cells there because we're going to drag the cells down. That's just an Excel thing. So we're basically taking the dot product of the AR terms with the past 6 values. So the red rectangle vector with the blue rectangle vector gives you this number. And then we need to add the intercept or drift term. So let's add that. Make sure you lock it in so we get that. And then we need to add in the AR12 term. So this AR12 term is basically the seasonality term. It basically helps us factor into the model an understanding of 12 months ago, what was the value, and if there is a pattern between 12 months ago to today, the model's going to learn that. And that's how seasonality is encoded in the models. The lag from 12 months ago is basically a 1-year seasonal lag. So I'm going to include that. And to make sure we get that right, we need to go back 12 months. So that'll be the value here, this 32.5 million. So let's click that. So we have our AR term, seasonal term, AR12, green, multiplying this B54 cell, which is the value 12 months ago. Let's hit that. So now we have our Y hat, right? This is our Y hat value, which is basically just drift plus beta 1 times, Y minus 1 plus beta 2 times Y minus 2 and so on, right? That's what the model is. It's just a linear combination of the past values with a drift term, which is just the intercept or coefficient, and with a seasonal term that is basically just another coefficient, but multiplying the value 12 months ago. So now I'm going to drag this forward into the future. And one thing we see here is the values get a little wonky. It's not even trained yet. It's just using random coefficients. But what we have to notice here is if I click this one, it's missing values, right? So if I click this guy, it's missing that stuff because the future is not complete. This is using the actual values to regress on. So what I'm going to do is I'm just going to copy what the model's saying and put it there. And basically what this does is if there are historicals, we take them, but if there aren't, like over here, we're going to take our predicted values as the prior historicals. That's what you're supposed to do, because you can't, if you're trying to keep rolling the forecast forward, you're not going to have historicals forever. So you replace the historicals with your predicted values as you roll forward, essentially. So there's our forecast. I'm going to graph it now because our chart doesn't have it on there yet. Oh, does it have it? What is this curve? Oh, right. No, that's correct. Okay, so now I'm going to add it. It's obviously not complete. Okay. It's going to look ridiculous, which is fine. And I don't know why I have to do this every time. It's kind of annoying. Okay. So yeah, I mean, the chart looks stupid, but we're going to fix it. So let's do legend across the top. So we have our revenue with the forecast, and we're going to fix it up. So back to here. Okay, so how do we train this? Well, we basically need to estimate what these coefficients should be, right? That's what we need to do. So for that, we need to construct an objective function or a loss function. So what's that going to be? Well, we're basically going to construct predicted values minus predicted values minus actual historicals squared and summed. That's what we're going to do to construct a loss function, right? It's very OLS, right? Ordinary least squares or whatever. There's always the predicted values minus the actuals. Take the difference, square it, sum them up, and that's what you want to minimize, right? So for that, it's pretty simple. Here's where our actuals, let me highlight it in orange. This is the last value of our actuals, last actuals value. Okay. Oops. This is our last actuals value right here. So what we want to do is basically fill up, sort of simulate what the model would give for past months, and then take the delta of the predictions with the actuals. So very simple. I'm just going to drag this up, and let's go, I don't know, let's go to like the beginning of 2017. Okay. So now this model is giving a prediction for, June 2019, where we have an actual value, right? And so I can take the delta. The delta will give me how wrong the model is. And in this case, the model is pretty wrong. It's off by about 29 million. So what am I going to do here for the objective function? Well, I'm going to say, take the predicted values, which are all these, and minus the actuals. We're doing like a vector minus, right? So here's all our residuals in a column vector over here. And then we're going to sum this, but we're going to sum the squares of them. So we're going to square all of those and then sum the result. We get a single number, which is our loss function. And what we want to do from here is minimize this loss function. And to do that, we can go into data and use the solver method. So the solver method in Excel is basically what allows us to do sort of advanced data science modeling in Excel without using Excel libraries or packages. The reason is because many times in data science, you're going to construct some kind of a model. It could just be a model that you're using sklearn for or something, or something else, but you could do something more custom, like maybe you're running a simulation and in the simulation, there's a output and you want to optimize or train the model so that the output matches real data, and then you can use it on new data. The point is you're always constructing these objective functions, and then you have to optimize them. The point is, once you optimize your objective function, you're basically constraining your model to reproduce real data, and then you could do cross validations on it and all that stuff. But basically, once you tune your model that way, you can then confidently use it, right, to make predictions or forecasts or whatever. So Solver can be, if you don't already have it, you can go into File Options, and then you go into Add-ins, and then Solver will be in here somewhere. And then here, I have it here. So you would add it in through this interface of add-ins. I've already got it added in. But anyway, I'm going to click my objective function value, go to Data, Solver. I want to minimize this value by changing variable cells. Which ones? All of these. I want all of these to be, I want Solver to search the parameter space of all of my coefficients such that it minimizes my objective function. And in this case, we can use the GRG nonlinear. This is a sort of a sum of square loss function, so it should be relatively smooth. It doesn't have to be, though. There's other options in here if you have different sort of problems, but the GRG nonlinear should be fine for most situations. If you have a discrete problem where your inputs are not continuous, maybe they're discrete integers, you'd probably want to use the evolutionary one. But anyway, let's go ahead and hit solve on this. So it says solver has converged to a current solution, all constraints satisfied. Great. I'm going to keep the solver solution, hit OK, and now I can see that my coefficients have been updated, they've been changed. My loss function is now smaller than it was, and if I go back here, I can see, generally speaking, that my forecast is pretty close to my actual revenue, right? As I scroll down, these numbers are pretty close to each other, which suggests that my model has been tuned properly, right, to fit the information. So that means that these coefficients have now been fit or estimated from real data. And so now this model is legit, and going forward, I have a forecast. Going forward. So if I go back to my chart now, this is my forecast. And so you can see where the blue line, so let me rename this to revenue actuals. So revenue actuals, let's just abbreviate it to be consistent. Rev actuals, rev forecast. So you can see that where I have historical actuals, that my forecasted value, which is basically my model, is doing a pretty good job at estimating those information. So that's really the fit. That's the fit of the model to the data. And then you have the forecast, which is the values in the future for which there's no there's no blue value, essentially. You can see that the forecast looks like it makes sense. It doesn't look crazy. This series was an increasing series, so clearly that makes sense. It looks sensible. It looks like it makes sense. It's propagating the current dynamics into the future. So it looks like a very sensible forecast. So that's basically the method. Now, the cool thing about doing this in Excel is that I can easily tune this if I want to. So you can see that I've estimated the coefficients on data going back to the beginning of 2017. But what if I wanted to do this like using all the historical data? Maybe I want to do that, right? So what I would do is I would drag this up to the top, and I can't do it for all the data because it won't be able to compute. Yeah, it can't compute beyond a certain point because there's no AR12, right? So you need to truncate some of this. But let's say I'll go back to the beginning of 2017, and now I go back to my loss function, and I make sure that my loss function is including all that information going back to 2017, which it seems to be. Okay, I guess I didn't have to update that. Cool. So let me hit solve on this again. So it's got all the same stuff. We hit solve. There we go, re-estimated, and now it's gone a little bit back. I don't even know if it changed actually. Did it change? That's weird. Did I do something funny here? Let me see. Okay, I'm not sure what happened there. But the point is that we can, let me drag this up. So I'm dragging the loss function calculation up, and I'm going to hit solver again. Let's go ahead and run that. Great. Okay. And now I get maybe a possibly more stable forecast. This series is much more predictable, so using more of the data kind of makes sense. There's no major glaring issues in the history, so maybe this is fine. Now, let's say, you thought this growth was too much and that you expect that it won't ever quite exceed 70 million per month, let's just say, which the forecast shows that it is exceeding 70 million when you get out into 2022. So how might we fix that here? Well, it's very simple actually. So what we can do is we can say in our objective function, we can penalize values that exceed 70 million, right? So here in 2022, we're saying that we shouldn't really be over 70 million. We should kind of stick or hover at 70 million. So what I can do is I can say, this is just one way to do it. Like, what is the average 2022 revenue? Well, let me just calculate it from my prediction data. It's going to be this. Okay. So now, let's say I scroll back up here and I say, okay, I want my objective function to penalize it whenever it sort of goes above. I'm going to use, let's look back at the graph for a second. What if it goes above 60 million? I want to penalize it, right? So in other words, what I want to say is here's my objective function. I want to add a bias to it or a further constraint that's going to be 60 million minus this, okay? So now it gives me a different objective function, 60 million minus the 71 million, and I'm going to square it. And I'm also going to have a regularization strength. Let's just give it a value of 10. So something needs to multiply this, so I'm just going to use 10 for now. So here's my new loss function. Now it's what it was before, but this time it also has a penalty term on the output of the model. So the output of the model for the year 2022 is biased towards being 60 million. So let's see how this changes the value. I don't even know how it's gonna. Let's just see. So I'm gonna do the same exact thing. Hit solve. So we have a new model. Let's go back up to the forecast. And now you can see that it's decreased the forecast, right? So before we were up in the 70s going into the 80s, but now it's sort of shrunk the forecast down, and now we're kind of actually, it looks a lot more realistic to me when I look at this, given the growth rate trends and stuff. So the coefficients now have been estimated the same way they were before, but with the extra penalty that we want the 2022 average revenue to be more like 60 million instead of being 70 million. So that we kind of crafted the output a little bit, but still within the framework of auto-regressive time series models. So this output looks much better, and I would choose this if I was to serve this up to, upper management or whoever is going to be using the forecast. I would actually use this method, and I would probably do some sort of parameter sweep and give a range or something. I would end up doing something like that. But if I was asked for a quick forecast of this, I would do this in Excel in the same way I just showed you, and I would be crafting the objective function to sort of give me something that's sensible and realistic, right? So if I was doing this in real life, maybe this this target of 60 million, and now you can see this value has updated to 61 million because it's been constrained. So maybe I got that from market assumptions. Maybe I'm the data scientist doing the forecast, but I still do my research, and there's obviously industry experts in whatever industry I'm in that are creating projections and who understand the industry very deeply. And so we can take their forecasts and their outlooks into account by modifying our objective function so that, we're still very much data driven. That's all given by this part of the objective function. We're still data driven. We're respecting the historical seasonality patterns, everything about the series itself, the growth rate, the drift term, but we're also making sure we include business sense and knowledge from the industry by constraining the objective function further so that it gives us output that's the most realistic and our best guess at the time. So yeah, there you have it. Sensible forecast in Excel. And let me actually, can I move this down? Is this going to work? Yeah. Let me just shrink it a little bit, put it all in one little view here. Let me zoom out a little bit. So yeah, there you have it. This is a quick and dirty, yet still very powerful and effective time series sort of forecasting method in Excel using the solver method and Excel formulas. No external big giant packages needed aside from the solver, which ships pretty much standard with every Excel. But yeah, I hope you guys found this useful. But yeah, you'll arrive at a sensible forecast, tunable by your industry expertise or that of others that you can factor in. And I hope this helps you whenever you need to go forecast something. You can kind of spin up a quick auto-regressive forecast very easily and include important, business context. And I didn't even say I should have included that we can include exogenous regressors as well. We can include exogenous regressors as well into this model very easily. Right, so we have the betas, auto-regressive terms multiplying, the past values. There's no reason why we can't have, beta 1, beta 2, beta 3 that multiply. Maybe you're multiplying GDP, maybe you're multiplying the unemployment rate, or maybe there's some other series that's important to your business, like new home sales or something, who knows, but we can factor these in the same way into the y-hat model here. It would just be more terms, and we can optimize them the same way, and yeah, it's still pretty useful. So I hope you guys found that useful, and I'll be back again with another video soon, but hopefully this helps you at work. Till next time.